All right, let's talk about a really common problem in calculus. You run into these differential equations all the time. They model everything from electrical circuits to sound waves. But what happens when you get one that just doesn't have a simple off-the-shelf solution? Well, you don't give up, you get creative. You actually build the solution yourself, piece by piece. So let's dive in and see exactly how that works.
So here's what we've got on tap. We're going to start with why we even need a method like this. Then we'll get into the core idea behind it, which is pretty brilliant. I'll lay out a step-by-step recipe that you can follow, and we'll test it out on a simple equation first. Then we'll see how it handles something a bit tougher, before we wrap up by visualizing what our solution actually means.
So here's the deal. In physics, in engineering, you constantly run into linear differential equations that don't have what we call a closed-form solution. And all that means is you can't just write down a nice, simple formula for y using the functions you already know, like sines, cosines, or exponentials. There's just no neat and tidy answer waiting for you. So the big question is, what do you do then? Do you just throw your hands up? No way. Instead of looking for a function that already exists out in the wild, we're going to build one from scratch. And the way we do it is actually incredibly elegant.
And that leads us to the big idea here. It's a really bold assumption, but trust me, it works wonders. We're going to propose a totally different form for our solution. The core idea is this. We're going to assume that our mystery function y can actually be written as an infinite polynomial. We call that a power series. Seriously, think of it like building something with Legos. Each little term, like c naught, c1x, c2x squared, is just a simple basic block. And we're going to use an infinite number of these blocks to construct our final solution. And this formula, this is basically our master key. We're making the assumption that our solution looks like this, an infinite sum of terms, where each term has some coefficient, c sub n, and a power of x. Our entire mission, from here on out, is to figure out the rule, the pattern that tells us the value of every single one of those c sub n coefficients. Okay, I know that might look a little intimidating, but the process is surprisingly methodical. It's literally like following a recipe. And for a huge range of these linear differential equations, if you just follow these steps, you'll get to a solution. Let's break it down. Okay, let's walk through the recipe. Step 1, we make our big assumption. The solution is a power series. Next, we just differentiate it to find y prime and y double prime. Then we plug all of those series right back into the original differential equation. Now, this is where the real work starts. We have to massage the sums a little bit so that every term has the exact same power of x. We do that by shifting the indices. Once they all match up, we can squish everything together into one single series. And because that whole thing has to equal 0, it means the coefficient for each power of x also has to be 0. And that right there gives us our grand prize, the recurrence relation, which is the key to everything. Theory is great and all, but let's see this recipe in action. We're going to solve an equation that we already know the answer to, just to prove to ourselves that this whole thing actually works. Let's test this out on something simple. Y prime, y equals 0. Now, a lot of you probably recognize this right away and know the solution is y equals c times e to the x. Perfect. Let's see if our fancy new series method can give us that same answer. So we start by assuming y is a power series, and then we find its derivative, y prime. So after we plug our series for y and y into the equation, we get this. Now, see the problem here? Look closely at the powers of x. In that first sum, we've got x to the power of n minus 1. In the second one, it's x to the n. We absolutely cannot combine these two sums until those powers of x are identical. So how do we fix this? We do something called an index shift. Let's just focus on that first sum for a second. We're going to introduce a new index, let's call it k, and we'll just set it equal to n minus 1. That means, of course, that n is just k plus 1. So now we can go back to that first sum and replace every n minus 1 with a k and every n with a k plus 1. The table here shows you exactly how it works. X to the n minus 1 becomes x to the k, and ncn becomes k plus 1 ck plus 1. And just like that, both sums have the same power of x, and we're ready to combine them. So once we've combined the sums and set the new coefficient of x to the k to 0, we get our recurrence relation. Now, this isn't the final answer itself. A better way to think of it is as the engine that's going to generate our solution. It's the formula that tells us how to find every single coefficient as long as we know the one that came before it. And for our example, this is it. It's actually kind of beautiful, isn't it? So simple. It just tells us that to get any new coefficient, you just take the one right before it
and divide by its new index plus 1.
All right, let's put this little formula to work and see what happens. C1 is just C0 divided by 1. Okay, then C2 is C1 over 2, but we already know what C1 is, so that's C0 over 2 times 1. For C3, we get C2 over 3, which becomes C0 over 3 times 2 times 1. Are you seeing it? Come on, you see the pattern here, right? It's a factorial. The general pattern is that the kth coefficient is just our starting coefficient, C0, divided by kth factorial.
And this is the magic moment. We take that pattern we just found for CK and plug it back into our original power series assumption. And what do we get? We get C0 times the sum of x to the k over k factorial. And that, well, that is the famous Taylor series for e to the x. The method worked. It worked perfectly. Okay, so we've seen this method works for a simple case, which is great. But its real power, its real value, is in solving equations that don't have those nice, simple solutions. So let's take a quick look at a more advanced example, something called Airy's equation, which is super important in fields like optics and quantum mechanics.
This is Airy's equation, y double prime minus xy equals 0. See that little x multiplying the y term? That one little change makes this equation way more challenging to solve with standard methods. But for our series method, it can handle it, no problem. You follow the exact same recipe. Assume a series, differentiate, plug it in, shift the indices. What you end up with is this recurrence relation here. Yeah, it's a little more complicated. It connects each coefficient to the one 3 steps before it, but the principle is exactly the same. This process is literally how we define and work with these so-called special functions, like the Airy functions, that are essential in modern physics.
Okay, we've been pretty deep in the algebra weeds here, finding these infinite series and recurrence relations. But what does the solution actually look like? I mean, what does adding more and more of these terms to our sum actually do for us?
Here's the key takeaway. Think of our series solution as a sketch that gets more and more detailed over time. The first few terms give you a pretty rough approximation of the function, but it's only really good right around your starting point. But then, as you add more and more terms, your sketch becomes more and more accurate, and it's accurate over a much wider range. Each new term you calculate refines the picture, bringing it closer and closer to the true, perfect solution.
And that's really what's so cool about this. The series solution method isn't just some abstract classroom exercise. It is a fundamental tool for pushing the boundaries of what we can solve. It lets us define and understand solutions to really hard problems in quantum mechanics, optics, fluid dynamics, and so much more. It basically turns the word unsolvable into, well, we just haven't found the right pattern yet.